Okay, I want to kind of go through this business with implicit differentiation. So our schedule today says, our schedule today says 3:8. I'm probably going to work a little way into 3:9 as well. Let me ask y'all something. I would presume we've got 4 exams. The first one I think comes up Tuesday. I would presume that you guys would like to have review sessions. That would be helpful to y'all. I've got to do it in the afternoon or evening, depending on whether I've got something else going on. So when is good for you all in the afternoon? I know some of you are taking some classes in the afternoon. Okay, yeah, let's do it. Let's get them one bridge at a time, right? Monday will be the perfect view session because it's on Tuesday. Does anybody have any restrictions? Right. Yeah, and I'm sorry about that. Hopefully you can get your boss to kind of work with you on this. So what would you think? Oh, right. But of course, the review sessions, you want them to be the day before. Yeah. So what are your all's evenings? Like by evening, I say like 5 o'clock.
We're sitting in the same room, we usually just hang out.
After 1, right? Because the class you talk about is until 4:45. Okay, that sounds good. So it might be just me. So let's tentatively say, 3 o'clock on Monday. And the reason I say 3 o'clock is because your TA's got office hours too, so it gets you the whole day to take advantage of everything. I'll try to get something set up. Of course, I've got to go through the channels to get rooms, which I'm sure they'll let me know if Monday review session or in 2 weeks. So we might just have to chat with me, but anyway, there's a mostly empty class next to my office. So I'll start that off by saying that. I'll try to get that set up. Let me tell you what my review sessions are like. Any question goes, but I do it unstructured. So you guys got to bring questions, but we'll hit it. I've got a zillion and one old exams. I looked at on my website and so forth. So we'll just do a lot of problems. Okay. The last thing we were talking about after we kind of reviewed over the chain rule is this business about implicit differentiation. So the idea is have equation involving x and y and unknown function. So you have y z of x implicit. So you have some equation that involves variables x and y, and you assume that y is a function of x. You may not be able to solve this equation very well. And so how do you take a derivative? or how to find y prime any. This is the whole idea behind it. Let me give you an example. This example later. Yeah, this is what actually quiz, and I'm gonna write it. By the way, you probably know this. I don't think there's any reason that you should. When you get into 1080 later, you'll figure out some techniques to do this. I have to figure out what this looks like, but this is actually fairly common, even though this looks sort of like a simple polynomial, it makes kind of a mess. I'm gonna write a picture of what this looks like just for fun. By the way, does anybody know this? There's sort of a symmetry. Notice if you reverse the roles of x and y, if you replace every y with an x and every x with a y, what happens to this equation? You get the same thing, don't you? Does anybody know what that means about what this looks like? When you replace, does everybody understand what I'm saying? When you, if you take every x and replace it with y, this equation, and every y replace it with x, you get the same thing, don't you? Yeah, there's a symmetry to it, and what this means is this thing ends up being symmetric about the line y is x. And so actually what this thing looks like, I'm not going to something like this. That's what this thing looks like, more or less. Now, is this a function? No. Can you tell me kind of a key place that you can see that this is really? You have some big problems. Vertical line is. You can solve this for y though. Anybody know the cubic formula? It's a mess. I'm gonna have to take my notes here. I actually solved this. There's a number of ways that you can solve the cubic formula. Here, you write y is equal to, if you solve this equation, the cube root of minus 1/2 x cubed plus the square root of half the square root of x to the 6 minus 32x cubed plus the cube root of minus 1/2 x cubed minus 1/2 times the square root of x6 minus 32x. Obvious, right? Yeah, not at all, right? I mean, who knows what order I pulled this out of? This happens to be true, but there's a couple of problems with this. Number one, how do you solve this in the first place, right? That's problem one. Problem two, suppose I just gave this to them, right? Who wants to take a derivative of this? Nobody, right? This is just awful to take a derivative of. Everybody on the page with that. And number three, as I pointed out, this isn't even a function. So this can't, whatever this equation is, can't represent this whole thing. What does it look like? I mean, I don't even know what part this is. Is it this part right here? Is it something more? Is it something like this? This piece right here, which one of these is it? Is it any of them? Who knows? Right? So if I want the tangent line right there, If this thing represents this piece, I'm not gonna be able to find the tangent line right there because it's not even in scope. Okay. So there's myriad problems, right? Solving the equation, taking the derivative is awful, and I don't even know what piece of the function it corresponds to. Remember the example last time with the circle? That was easy, right? Because you had two pieces of the circle, the upper and the lower, plus square root minus square root, right? Here, I'm not sure. So there has to be a better way, right? Nobody wants to try to solve it. Fortunately, there is. Let me give you another example. I'm gonna work with this one. Yeah, but you're going to work with this later. Let me give you the following example here. Consider the equation x4 plus y2 plus 2x y squared c. Find things are fine. To curve, find out this. Have okay, let me start by saying there's something wrong with my problem. This is not a good problem. In fact, it's wrong. The problem is not really the equation. If I'm going to draw, I don't. So this might draw some kind of fancy curve. If I'm going to draw a tangent point, it has to be on the curve. Is this point on the curve? Yeah. It's just like being in a chemistry class. It doesn't balance, right? What happens if you put in one for x and one for y? There's no way the left-hand side and the right-hand side are equal, right? Because that's 0 and this is positive. Right? This is the real problem. Oh, I better check it out. What happens if I plug in -1 for x and 1 for y? -1 for x, that's an even power. So I get 1 here. I get 1 here. And then I get 2 times -1 is 20. Okay, so everybody agrees this point is on the curve. All right, so to find the tangent line to the curve, I need to, well, what's the tool I need to find tangent? That's exactly right. So to find any line, I need 2 pieces of data. I need a point and a slope. Everybody agree with that? Got my point, there it is. It was just given. I need a slope, and to get that slope, I need, as you say, the derivative, right? Now, of course, in the old days, when you had explicit functions, you had y as f of x, y is sine x, y is x squared, something like this. Here we've got this awful equation, and nobody wants to solve for y or for x, right? It's terrible. But what can we do? Well, let's write my equation down. Now, you need that derivative. How are we going to shake a derivative out? This is a wonderful thing because it always works. Take a derivative with respect to x, just like you're in the calculus. Now let's go through this. When I take the derivative of this side, what's the derivative of x to the 4? Okay, good. Hey, how about this? It's like, yeah. Am I done with this? Is it just 3y squared? It's 3y squared, y prime. Okay, good. I'm glad you asked that. Okay. What is the derivative? See, always been kind of do it over here as well. ddx, right? We're taking the derivative of x. What is the derivative of blob to the fourth power? It is 4 blob cubed. And what does the chain rule tell us to do? Derivative, we got to multiply by the derivative of whatever's inside the parentheses. Agree? What's inside the parentheses? X. 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 And that's just the 1. So this is just the whole negative 4x. Let's look at the y. Y is not, we're not taking the derivative with respect to y, we're taking with respect to x. This requires a chain rule because this is actually shorthand for a function of x. Right? The derivative of sine x is not 1, the derivative of sine x is cosine x. Same principle here. This is 3 blob squared. And are you done? You got to multiply by the derivative of what's inside. What's inside this time? The y dx. This is what I'm calling y prime, and it hangs around. Right? The dx is gone because it's already in terms of x. Because dx is 1. dy dx, it's not necessarily. Which one? This?
Yeah, why did
This is the derivative of x with respect to x. This is the derivative of y with respect to x. Right? So what's the derivative function of x? There you go. What's the derivative function of sine x? Not 1, right? Because it's different. It's the same principle here. X is like x. Y is something more exotic, like maybe cosine x.
always why?
Right, and I've been writing this y prime, but of course, what's the same as dy dx? So this right here is 4x cubed dx dx. I'm a lazy man, so I just left it at 1 instead of writing dx dx. It's 3y squared dy. So let's, and while we're at it, let's tackle this one. Okay, so what is, this is a product rule, right? So this is 2 dx dx times y squared, right? And then this is 2x times the derivative of this is 2y to the 1 dy dx. And the derivative of the other side, see? So what we have here, translation, this is 2y squared plus looks like 4xy y prime. Everybody with me? Okay, now what the heck did I? Oh, yes, yes. So I'm looking for the tangent line, the curve, find by this at -1. Okay, so now I have an equation. My equation now involves three things. It involves an x, it involves a y, and it involves y prime. And y prime is what we're searching for. Right? What do we need to, what do we need to do now that I've got this? That's sort of my calculus step right there, just taking that derivative. Now what do we need to do? Well, I need a number for this. What's it? Okay, that's even better. One of the things that I can do is I can solve for y prime. But that's sort of dubious work because I don't really care about what y prime is except at this point. Now notice in the old days when you just had y equals f of x and you took the derivative, you only had to plug x in. Here you've got both x and y, so you've got two things to plug in. Let's plug in x equals -1 and y equals 1. And what I get is -4 plus 3y prime plus 2y plus 2. And let's see, 4 times y is 1 is -4 y prime is equal to 0. Everybody agree with that? Plug in values x equals -1 and y equals 1. And this gives me something that I can solve for. Right? In fact, what I get is -2 minus y prime is 0, or y prime is 2. Everybody okay with that? So tangent line. I was just do point slope form. Y minus 1 is -2 times x minus minus. And there you go. Any questions? Now, one other thing, notice we shortcut our work on plugging in. Let me sort of add an addendum problem. What if I had been asked this question here? So let's go back to this equation here. 4x cubed plus 3y squared y prime plus 2y squared plus 4xy y prime is equal to 0. Now, my question now is find the formula for y prime. All right, I didn't need that. I plugged in the numbers earlier, previous problem. I only needed to know what y prime was at one specific point. But what if I want a formula for this? The cool thing about this is if you're patient, you can always do this. How am I going to find y prime? So this is really this algebra question, really not a calculus. Just divide and conquer. Put all the crap with a y prime in it on one side of the equation, all the crap without a y prime on the other side. So let's try that. Now, what's a good strategy here? That's right. That's the whole point of sort of putting the y prime stuff on one side of the equation. Now, So I get y prime is equal to. Right, and of course, at this point, you could also plug in the -1 and get negative 2, that's more steps. But this gives you a formula for y prime, no matter what point x and y you find on the curve. Question. Okay. The whole one. I think I was mistaken about it. What is the derivative of e to the x? Okay. Okay, I gave you an equation there. Find me a formula for y prime. And let's have a friendly contest. We'll race. See if I can. bet. I agree. Yes. This is more fun. That's. Oh, you brought that up. So. So now you're. Right, so see. So. So, what is this? So you can put it over. Right, so that was me first. See if that. Anybody hit an impasse? It doesn't quite look like, it looks like you got pieces there. Okay. Good news. Yeah. That's the piece. Right. So set that up there. Yeah, so really. All of these really have that more cost out. That's what we want confidence and so that. That's the same deal. And I think that's good. I think that's kind of the same shit. So it looks like you pull the how do you pull that stuff? It's not. Okay. Let me check on these guys. Maybe we just kind of go over. How you guys getting along? That as well. So let's go over this. So the first thing I'm going to do is I'm going to, now that I've seen what y'all are doing, let me do one cosmetic thing. This. Here's my cosmetic thing. Now, let's take the derivative of this. Actually, you're over a big part of the mountain if you got the calculus step right. And this is the calculus step. After the calculus step, it's algebra, which you have to be good at, but it's a sort of a lesser thing at this point. What's the derivative? X to the 4. Okay, good. Okay, now this one for sure is going to require a chain rule because I've got some blob going on. Right, so that's gonna be 1/2 log minus 1/2. But I'm not done. What do I gotta do? Multiply by the derivative, whatever I find inside, which derivative, that thing. Derivative of x squared is 2x. Derivative of y squared is. Okay, now the other side, this kind of throws some people. First of all, the first thing I come to, this is another chain rule because it's e to some block, right? What is the derivative of e to the block? That's one thing I just totally did on exponentials. It's the same thing. But the chain rule says you're not done yet. You got to multiply this by the derivative of what you find inside. In this case, x squared y. And I'll write that below here. What is the derivative of x squared y? Well, this is a little product rule, isn't it? Right. So derivative of x squared y plus x squared times the derivative of y, which is so let me clean this up a little bit. This is 4x cubed plus 1/2 Here is the unfortunate part of this. This is just kind of a messy Brunswick thing. Since I did actually find y prime. Here's the problem. You've got a y prime here and a y prime here, and they're in parentheses. So you're just going to have to bite the bullet and multiply that. So this is 4x cubed plus, let's multiply this term first. The 1/2s cancel, and I get x times x squared plus y squared minus 1/2. That's this times this term. And this times the other term is, again, the 2's cancel, and I get y x squared plus y squared minus 1/2 y prime. The other side, I'll just multiply this through. Now, I've got two terms of y primes. And so I'm going to do this here. Let's say I'm going to put the y prime stuff on the right side and stuff without y primes on the left side. So let's see. I've got an x squared, the x squared y prime. And I'm going to bring this thing over, join it. And on the other side, I've got 4x cubed x times x squared plus y squared minus 1/2. And I better bring this one over here. It doesn't have y prime in it. Plus 2xy e to the x squared. Everybody agree? That's just putting y prime stuff one on the right, not y prime stuff on the left. Now, all I gotta do is pull y prime out of that and divide. So I get y prime is 4x³ plus x squared plus y squared plus half plus 2xy x squared y over one messy formula. There it is. Okay, any questions? Oh, and I did make a mistake here. Anybody get on mistake? Yes.
Yeah, 2xy, x square y is negative.
That's right, absolutely. That should be a negative. Very good, good eye. Okay. I've got a little. This one, any questions? Understand? Okay, here's a fun problem. Find if I remember what this is. This is a circle. Some rate is R, centered at the origin. Okay. Find the first three derivatives. Double find. On the derivative, find its derivative. And actually, it peaks in hardness about in here. So Okay. Well, let's go back. It's too hard, but ours, what's the rhythm of the constant? There you go. It's what it is. So so now. And then take another. No, it's not quite right. Let me get you all started on this. So, to answer the first question, yes, we do. Okay. What's derivative of this? What's the derivative of Westwood? Good. What's the derivative of Arsenal? R is a constant, right? Or if you like, if you want to be really dramatic, but the derivative of constant is zero, this is a big fat zero. So now what you get is 2x plus 2y prime is 0. Now solve for y prime. And that'll give you the answer to this. And verify it. See if you can solve it. But there you go. Now press on. I will give you a hint on number two. Notice that number one, I've got a formula that involves both x and y. If you do number two right, you will have a formula that doesn't involve x at all. Only involves y. You will at first get stuff that involves x and y, but there's a way to get rid of these. My hint is the original equation. Yes. Oh no, you can have a prime on any level, right? So 2r prime. Let's see, r is a constant. What's the derivative of the constant? Well, the reason you know it's a constant is because I said at the beginning of the problem, it's a circle, x squared plus y squared is the constant radius r. But if there's any question in your mind on a test or whatever, if something's constant, just ask me. I'm not going to try to trick it that. Right, but yeah, r is a constant. It's a fixed radius. Well, the only reason I said r is greater than 0 is r. I want my radius to be a positive value. Actually, if you look at the equation, it doesn't matter if it's positive or negative. But I don't want the circle. I don't want r to be 0. I want the circle to be a constant. I want to be an honest piece. And I want the radius. But yeah, it's the constant. Technically, you probably I should include it. When you get y double, All right. Look. It looks to me like it's two different sort of points. And you know what, to make your life easier, I can't spell. So that'll. Yes. Well, that's. Oh. So. So, here's what you got. This is not even. Fun. Just solve. So you've got, now, you're stringing together a lot of things equals that you don't want to do. So let's search. So you're taking the rate, what you got in one. And use the quotient. Minus the top, which is X. That's. But take one. You want one. What is finding? And then use the original equation to see if you get it. You should get something that involves only y. And make the radius of the circle. Anybody figured out what y double prime is here? So what you have. So each side of the is minus x y minus. Derivative of this. So this is a derivative of minus x. What's derivative? What's derivative negative? Derivative of y minus 1 is minus y minus 2. What's equal? Now this is. Minus. Well, so here's another problem with that. This two was originally in the denominator as a double denominator. This should cancel and get down to 1. And now you put 4. You'll see that this two is in the denominator here, and then you sort of brought it up. It might be easier. Why don't you try that? So what y prime? That's what you got for the quotient. Try the quotient. bottom square. Bottom. Top of minus one. Minus the top. Times the derivative. But then, the place why, with this. See. Remove it. It's coming. So replace y prime, what you know this is. See, it's a normal false y. Yes. Oh, you're told. X squared is y squared is r squared. What's negative x squared minus y squared? Yes, y. Right on target. Pretty good. You're almost there. Multiply top and bottom by y. And I think. Yeah. Okay, folks, let's kind of go through this one. Let's get it up to the next derivative. Okay, that's what we had at the end of part one. How do I get the second derivative? Take another derivative. And so I'm going to choose to do the quotient. So it's bottom squared, bottom times the derivative of the top, minus top times the derivative of the bottom. Everybody okay with it? Now it's an unholy mess. That's y, that's x, y prime. Now, the problem with this, I mean, this is really correct, but I can do better in the following sense. If I want to figure out what y double prime is, I need to know three items of data, right? I need to know what x is, what y is, what y prime is, right? But I can make that easier because I already know what y prime is. I can write that. So I'm going to replace y prime by what it is. Again with the unholy mess. This looks like that old Three Stooges fun fair. Three things on it. So I'm going to get rid of this y here. I'm multiplying top and bottom by y. We get minus y squared minus x squared over y cubed. Now, does anybody see this problem actually has a simplification? Because of the symmetry here. What's another name for that numerator, y squared minus x squared? Very good. Cos. So not only did I use the derivative in this case, but I used the original defining equation. Did somebody argue why the map? So let's look at a circle. Look at the first derivative. I'm gonna ask a couple of questions. There's a couple of circles here. That was a really bad circle, but that's actually. I'm trying to point about it metrically. Now, let me ask you a question. One I find strange is the y prime slope of the tangent line does not depend on what the radius of the circle is. Somebody tell me why that makes sense. Notice the second derivative doesn't depend on the radius of the circle. First derivative. These are two circles, agree? One with a smaller radius than the other. What should be true about the slopes of the tangents here? If I draw the circles better, the slope should be the same. These should be parallel lines. Everybody agree with that? And so that's why it depends only on minus x over y. In fact, if this is the point x, y, then right. If this is the point x, y here, then the slope of the tangent line, notice it's negative, right? Minus x over y depends only on ratio here to here, and this ratio is the same. Now, can somebody tell me what does the second derivative mean? The first derivative means slope of the tangent, right? What are you supposed to second derivative mean? We're going to talk about this more in depth later. The first derivative is change in the y coordinate, right? The second derivative is the change in y coordinate. So it's the change in the slope. Notice that this formula depends only on y. And notice if you have two of the same y coordinates, right? The slopes of the tangents should be changing the same. As you change x. Okay, what about the next step? Let's go. It actually gets easier here, I think, in a certain sense. 3. Squared over y cubed. So now let's just take the second derivative. Again, I'm going to square the bottom. Bottom times derivative top. The top is a constant, so it's derivative is 0. So the bottom times derivative top minus the top times the derivative of the bottom. What's the derivative of the bottom? Three y squared. So I can quite clean this one fairly quickly. The minus cancels. And I'll cancel y squared down to like this. So I get this. Now there's one more thing that I would recommend doing, and that is again replacing y prime by minus x over y. And so for the third derivative, I get, what do I get? Minus 3 r squared x. on y. I'm going to show you kind of a good composition. How many of you have your book or have access to your book? Anybody? I'm gonna draw you a picture out of your book. This is exercise 81, and I'm not gonna do 81. I have someone to do something different. Because I found something more fun. Here's my little book. We've got this thing drawn. It's called the some drawing of Pascal. And it was something like this. And 1, 2. Not drawing it as well because I think they ask you. I think they ask you in this problem, what's the slope of the tangent? They give you an equation, of course, and the equation they give you for this. The equation they give you is x squared plus y squared plus 2x minus 2x squared. And so for right now, you can take this just as a matter of faith that this draws this funny looking thing. And the 0.22 should be on it. So the 0.22, that's going to be 8 minus 4. 4 squared is 16, 2 times 8. So 2 times 8. So do this exercise, find out what the slope of the tangent is. Fun. But I want to do something else. I want us to find how many places. So I'm drawing that picture. How many places on that curve you think the slope of the tangent is 0? How many? 4 times. Everybody, does everybody see that? It looks, that's what it looks like to me. It looks like right here and right here. And then somewhere about right here, right here. Right here. What are the x coordinates? By the way, there's 4 different points. Everybody agree? What does it look like? How many different x coordinates are there? It looks like there's only 2, right? So for this x coordinate right here, there's high and low, and for some other x coordinate over here, there's high and low. Everybody agree with that? What are those x coordinates? But what do you want to be 0? What is actually 0? Not the y. Because y is 0 is along this line like this. It's the y prime, right? It's the slope of the tangent. So I need an equation that's got a y prime in it. If I want to find where the slope of these tangents are horizontal, I need to find a place where I need an equation that has a y prime in it. So what should I do? Take a derivative. That's right. Because when you take a derivative of this, I'm going to have an equation that's got some y primes in it. So let's see what happens. This is going to be, so my instructions are find x coordinates where slope of tangent is 0. Now, this is gonna look kind of depressing, but we're gonna have to go back to this. So, let's take the derivatives. What's the first thing I come to? Log squared, right? Now I've got to multiply by the derivative of what's inside. What's the derivative of what's inside? Derivative of x squared. Derivative of y squared. Y prime. Derivative of negative 2x. Set this up the other side. This is 2 times 2x plus 2y. Do I agree with that? Now I could go through and solve y prime. Right, it's all y that moment. But what's the key observation that you made here? What if we want y prime to be? We want y prime to be 0. So let's put that in there, see what shakes out. I should do something easier because some stuff's going to drop out. So here I'm going to get 2. Well, now it's just 2x minus 2. And here I'm going to have 4x. And that's it. Do I agree with it? I'm going to make this a little easier on myself. I'm going to divide this by 2 and this by 2, 4. So my equation is now x squared plus y squared minus 2x times x minus 1 is equal to x. How is this going to help? Let's see what it's out here. I've got this equation. I'm trying to find x. Notice it's got 2 variables and it's got y and x. And the only other thing I've got to work with is the equation. Notice that this gives me the x squared. Everybody agree with that? All I did is I divided both sides by x minus 1. Of course, I've got to be careful. I got to make sure that x is not 1, but there you go. Everybody agree with that? And if I wanted to manipulate this a little bit, notice that x squared plus y squared is 2x. Now it kind of looks like I'm having a stroke up here, right? Because I just see pushing stuff around. However, let's see how this helps with this equation. X squared plus y squared minus 2x is replaced by this as only x. Right? So I can replace this bit with x over x minus. Correct. And x squared plus y squared can be replaced by this bit that has only x. I agree with that. So let's see what this gives us. This gives us x over x minus 1 squared is 2 times 2x plus x over x minus 1. So x squared over x minus 1 squared equals 4x plus 2x over x minus 1. Now, if you were going to go about trying to solve this, what do you think is one of the easiest things to do? Or what might be something to do? Okay, who hates fractions? Everybody hates fractions, right? This is an obnoxious fraction. And anybody think something I can multiply both sides of this equation by get rid of the fraction? Good, good, good. Multiply both sides of the equation by x minus 1 squared. On the left side, this strips it down to x squared, right? I agree with that. On the right side, I have 4x, that's x minus 1 squared. And for this piece, 1 power cancels. I agree with you. Everybody, does everybody understand how x minus 1 fills us down to x squared? Goes through 4x. Oh, I realize that I have that x there. It's actually 4x, that's x squared, and then 2x. Does anybody see something we can cancel? Make it a little easier? There's a factor of something on both sides. Anybody see what it is? X. So I now can rewrite this way. X equals 4. X minus 1 squared plus 2 x minus 1. And so let's just kind of like what we're doing. When I multiply this out, this is 4x squared minus 8x plus 4. And this is plus 2x minus 2. And I'm going to bring x over. 4x squared. See, that's going to be minus 6x minus 7x. And constant again. And this is something I can solve with quadratic formula. 7 plus or minus the square root of 49 minus 32, 7 over 8. Now let me give you round figures on this. The square root of 17 is just a little bit more than 4, right? So this is about, with the plus root, this is about 11/8. So the price is top. If I draw this a little bit better, the tangent might be a little bit beyond 1. And with the negative root, it's at roughly 3/8. So I got sort of 2x coordinates. I see that. The hard part, again, this is the way calculus almost always is. The hard part of this is actually the algebraic. It was tricky to solve this equation, right? But the calculus step was actually kind of easy. Just that first step where we had the y prime step. Okay, any questions on this? Oh, because the equation that I had was this is actually the equation that defines this. And this right here can be replaced by x over x minus. And that's the same. I got rid of it. And see, the reason I did this is because this has got two variables, x, y, and this one. Okay. Can somebody, so I want to talk a little bit about kind of where we're going next. 3-9 here. Can somebody tell me what? Can somebody describe this function to me? Anybody know what it looks like? Okay. It does. That's right. There's a function that it's related to. Anybody know what that is? So the log x, as you say, goes this. It goes 2.10. Anybody know what it is the inverse function of? It's actually, that's right. If you flip this around the line y equal x, it looks like this, right? And this, instead of being 0.10, is now 0.01. In fact, probably when you first saw the natural log, you probably defined it as the inverse of the exponential. So, what do I mean by inverses? Well, I mean it's sort of a reverse gear. So, and this has an infinite tie-in. There's a reason I bring this up now when we talk about implicit differentiation. Logs and exponentials. What happens? Well, I'm gonna do it first. What happens if you take natural log of e to the x? So you take your calculator, put in a number x, you take the exponential, then you take the log, what happens? That's right, you get back to x. So the exponential does something to x, log reverses it, you get back to where you started. Right? Number two, what happens if you take the log and the exponential? Same, but there's a caveat. Does anybody know what the caveat here is? This works for every x. This only works for some x. What the difference is? That is correct. X must be positive because you can't plug a negative number or even 0 into a log in the first place, right? So what's the derivative of these? Idiots. Everybody loves brother idiots because it's his own derivative. Screw the log. Let me ask you another question. What's the derivative? So let me ask you, this is a little bit more good. What is the only power of x that you cannot see on the right side of the equation? So for example, if I wanted to see it 2 over here, I would just take the derivative of x cubed. The derivative of x cubed is 3x squared, and then I have a 2. If I wanted to see a -7 over here, I take the derivative of x to the -6. And the derivative of x minus 6 is -6, x to the -7. What is the only power that I cannot see on the right side? Now you can see that, because you could take the derivative of x, right? And that'll be 1, which is x to the 0. What's that? -1 is the only power that you can't see. Because what would you have to start with to get a -1? You'd have to start with x to the 0, but that doesn't work, does it? Because the derivative of a constant is just a constant again. Strange, isn't it? There's only one power missing. So here is a nice, wonderful application of implicit differentiation. Suppose you have the function y is log x. My question is, what is y prime? What is the derivative? Well, I don't know. But one of the powerful things about inverse functions and implicit differentiation is you can play a known off an unknown. So if I take e both sides, and here I'm assuming x is 0, of course. Then I get e to the y is x, right? Because e to the log x is x. Everybody okay with that? So check this out. E dx. Let's just do like what we've been doing all day long. What is the derivative of e to the block? Block. And am I done? Exactly. In this case, what's the derivative of the right side? So I've now got a formula for what y prime is. But this is a little bit unsatisfying because y was log x, and the derivative in terms of y doesn't make me very happy. I'd like some of that. But I can write this. See what's in one. That's right. Another name for e to the y is ordinary old x. And there's your missing power. The derivative of log x 1 over x. And that sort of completes, right? So here's a big theorem. Now notice this only works for the log function. The log function is only defined for x being 0. I can actually up the voltage on this, and I will. In fact, the derivative, the natural log of absolute value is also. I'm going to show you more carefully why this is true next time. But here's the advantage of this. Log x is a mild-mannered function that only the domain of log x. What numbers can you plug into log x in your own? It has to be positive, right? So this function is only defined positive values of x. This function, much bigger, much better. It is actually defined for all values of x except for 1. There's still one value, the natural log of the absolute value. This is not defined. What's that? 0. So this is defined everywhere except for 1. Let me give you one more. This is kind of a fun teaser, and it'll help you look at your homework from 390. That Well. Even yet, and in fact. No, actually, E is a special case. This is an 8 of X times natural automatic. But actually, it doesn't matter. Really, this is all you need to know. Because once you know this is just a translate. And you all told me this one. If you have a constant base and a variable exponent, there's your formula. Derivative of v dx is e dx, which is e to the exponent. Right. If you have a variable base and a constant exponent, there you go. Right. Here's a quick one I'm going to do before we take the quiz. What about these are the most evil of problems. This formula does not apply because the base is, and this formula does not apply because the exponent. How in the blue blazes are we going to take the derivative of that? Right? This is something brand new, right? And this is actually what science and engineering stuff, how we're going to take what we've got and take apart something new, right? Here's what we know. We know how to deal with constant base variable exponent. E to the n. We know how to deal with variable base constant. No problem. Now, what happens when we both move? Nobody wants to do a limit, that's for sure. And what is that? It's something like that, yeah. So here's the problem. You've got the moving exponent and the moving base, right? I hate this power system. Now, again, logs are something that maybe you're still on the couch in therapy having to deal with it all year. Log is now your friend. I'm going to take the log of those things. And you may say, Jim, why in the world would you take something that already sucks and make it double suck, right? Because look at this. If there's something magic about the log that makes this better, anybody tell me what it is? What do you mean by cancer? What can you do with this power? You can pull it to the front. This is actually a nice use of the log because it takes this awful thing and makes it a better thing. This, I don't know how to take the derivative of, but this I do because this is an old-fashioned, all-American product. All right. So let's ddx this. Okay, so what is the derivative of log y? 1/4. That's the rule we just used. And I'm not done because I got to multiply that by y prime. Good. What's the derivative of this? Well, it's a product rule, right? And it's all x's. I'm digging on that. So derivative of x is 1 log x plus x times the derivative of log x, which is x. So if I clean this up a little bit, y prime times 1/y is log x plus 1. So now I get y prime is y of natural log x. Now, again, this is a little unsatisfying because I've got y in it, but hey, no problem. Y is x to the x. So this is a truly new formula that you probably have not seen before. And the logs and implicit differentiation is how to do this. I mean, you're not going to guess this, right? What's the derivative of x to x? Well, it's x to the x times log x plus 1, right? Any questions? Logarithms give you a whole more empowerment. Because whenever you have variable basis and variable exponent, you log successively sometimes. Bring things down and get you what you want. Okay, we're going to talk more about this tomorrow. Any questions?